Hi, Dylan. Oh, don't have my ears in. Hi, Dylan.
Hi, Professor P.
How's it going for you?
Pretty good. How about you?
I just found out that one of my students in my face-to-face class at HCC has, actually, he's in a dorm that has been quarantined because of COVID.
I know a lot of people who are going through that right now.
Oh, amazing. It is absolutely freaking amazing. No, I have to contact somebody so that the person they were with, do I tell them to go get tested or not?
That's a good question. Yeah.
I mean, there's privacy issues and there's moral issues. I don't know how I'm going to have to be directed on that one.
Does HCC have like a protocol for it set up yet?
Yes. There's protocols even for the protocols, Dylan.
So much fun.
Yeah. Imagine, I mean, so much that we are going through that we haven't been through since I think it was 1917, the Spanish flu that happened there.
Yeah,
I mean,
the Spanish flu outbreak.
And you know, if we would just be smart, we would be like Europe right now and we'd be open.
Everything would be fine.
What are you going to do, Dylan? Are you having any problems with anything, Dylan?
Not really, but could I ask you a quick question about the lab?
Sure. Okay, I'm sorry. My mind, Dylan, is totally not on that lab. Which lab are we talking about?
The density lab.
Okay.
So I have the total mass of the water for each of my trials.
Okay.
But when it comes to finding the total volume of water, do I take the initial reading, which was 4.95, or?
Dylan, okay, you've got water, right?
Yeah.
Okay, so you kind of, you know what the density of water is, right?
Yeah.
Okay, so just to be sure, to check yourself, the weight should be about equal to the volume.
Okay.
So basically what I think you're starting with a certain, are you starting with a certain volume of water in there?
Yes, 4.95 milliliters.
Okay, so the second reading, what you're going to be doing is you are going to be putting another 5 milliliters in there, right?
Yeah, I think it's 5.
So what you're doing is you're subtracting what you're putting in from 0.
Okay. All right. I wanted to make.
And the weight of your 10 milliliters of water should be somewhere around 10 grams.
Okay.
Make sense?
Yeah. I wanted to make sure before I did everything.
I perfectly understand. You measure twice, cut once.
A good rule.
Yeah, absolutely. How's everybody doing out there? Pretty good?
Yep.
Yeah, can't complain.
Rebecca, you blew a quiz, Rebecca.
I know, I forgot.
Things happen. That's why I have 2 drops. Okay?
Thank you.
No problem. Things happen and we get along with them, all right? Ladies and gentlemen, my morning class got through single replacement reactions. So we're doing good. And I'm also noting that I'm having less and less people every week. Let's wait until we get to thermodynamics. See how many people show up then.
Is that a challenge?
It's a challenge. Definitely my summer class definitely said that was the hardest chapter that we had. So we'll get through it. They got through it. It's just a rite of passage. I once took a thermodynamics test when I was in college in physical chemistry. The average, and I am not kidding you this, the average on the test was a 28%. Nobody's making any comments on that?
Was it graded on a curve? Please tell me it was graded on a curve.
Yes, absolutely. I had a 68 and I ended up with a B on that test. It was absolutely, I mean, that was if anybody is in chemical engineering, the course you have to worry about is physical chemistry. That's the one, that is the course that is a make or break for you going on. Okay. Hopefully I got my PowerPoint in. Okay, any other problems, guys? Quizzes? Any questions about anything? Wow. I tell you what, you guys need to thank my summer course because they were the ones that did all the editing for my quizzes. I got their complaints and I fixed the quizzes because of it. You guys are actually, I'm looking through the grades and you guys are doing fairly well on them. I'm happy.
You seem surprised.
I am. Usually the quizzes are the thing that brings people's grades down. But you're doing fine, so that's a good sign, guys. Okay, 5:30, so I'm going to get started. And hopefully somebody that they need to join us, they will be here. We had 6 people this morning. We have 6 people this afternoon. So as I said, people are dropping, but we will wait and see when we start to get into new material, whether they want to come back or not. Okay, so what we're going to do, we're going to start with balancing chemical equations. Then we're going to get into double replacement. Using the double replacement, I'm going to explain ionic and net ionic equations. Then we're going to go to single replacement. Eventually, we're going to get into acid bases, which are kind of like double replacement, combustion, and addition synthesis and decomposition. Those last 2, basically all I really want you to do is be able to recognize them because there's no real way to predict what the products are going to be for those. So our good friend, just getting back to the basics, we just have to know that the reactants are on the left side of the equation. They're the things that get put together and undergo changes. The products are the substances that have undergone the change. They are on the right side of the arrow. Our good friend Lavoisier, matter is not created nor destroyed. So what that means to you, more specifically, is that the number of arrows of each atom on the left side of the arrow has got to be equal to the same number of atoms on the right. We're not going to make or destroy atoms here. So, the first thing you have to do when you're balancing chemical equations, what you have to do is you must make sure that all the chemicals themselves are balanced. Do you remember what we went through with the plus charges and the minus charges to make sure that the subscripts are right? You got to balance the chemicals with subscripts first. Then don't ever change the subscripts. The molecules must be neutral before we start balancing the chemical equations. Remember, they're balanced with subscripts. Remember, guys, this is another thing. If I react calcium chloride somehow with sodium, such that I make sodium chloride. Calcium chloride is CaCl2. You do not carry the subscript over to the products. You don't start with NaCl2. That doesn't happen. What I'm going to want you to do is I'm going to want you to first predict the products, Then by predicting the products, just put them together. Then once you have the products together, I want you to then balance the chemicals. If you change the subscript, you change the molecule. All right, once the chemicals are balanced, you have to understand that the equations are balanced with coefficients in front of the molecules. And when we were counting atoms, guys, the coefficient multiplies with the subscript to give you the total number of atoms that that particular compound has. If you have no number, assume it is 1. Again, number of atoms is the product of the coefficient times the subscript. All right, I don't care what system you use. If you came up with a phenomenal system, fantastic. That is absolutely great. If you came up with a great system, use it. The thing about balancing is it has to be systematic, because if you're not systematic, you are going to go kaflooey in many more ways than one. What I like to do is I like to balance my cations except hydrogen first. Then I balance my anions except oxygen next. If you get a polyatomic ion that doesn't change going left to right, say you're reacting sodium sulfate with barium chloride. What happens is you form barium sulfate. The sulfate itself doesn't change from left and right. Treat it as a unit. Then when we balance the cations and anions, we balance the H's. And pretty much at that point, pretty much everything's balanced. If necessary, balance the O's and recheck everything. So we have an equation up there. All right. Balance the cations except H. I got a 1 coefficient in front of NaOH, no subscript. So that's 1 times 1, I get 1 Na. On the other hand, on the right side, I have 1 coefficient times 2. What do I have to multiply 1 by to equal 2, guys?
2.
Thank you. So what we do is we put a 2 in front of the NaOH. All right. Now, I said treat the anions as a unit. The SO4 hasn't changed going left to right. Just checking to see if anybody has joined. The SO4 doesn't change from left and right, so just treat it as a unit. How many SO4s do I have on the left, guys?
1.
And the right?
1.
I don't have to worry about it. Now, I cannot treat the OH as a by itself because it has changed. The OH has made the molecule water. So I have to treat the that O and that H separately. All right. Now I'm going to balance the H's. Let's see if I did this. Yeah. I'm going to balance my H's. I got 2 H's, and I got this coefficient times H with the 1 subscript. 2 plus 2, I got 4 H's over here. What number has to go in front of the water?
2.
2. So I get the 2 in front of the H's. So I have that. Now I got to look at my O's. I got 2 over here, 2 times a 1 subscript. So for 2 oxygens over here, I got a 2 coefficient times a 1 subscript over here. That's again 2 oxygens. I'm balanced. Go through and check everything out. And the reaction is completely balanced. This works on simple equations. This will not work on complicated redox equations, but it works for the time being. All right, Dylan,
Yeah,
how many aluminums do we have on the right
2,
and on the left?
1,
So fix it. What do you have to put?
a 2 coefficient.
So 2 on the left, you put a 2 in front of this one. 2 times 1 gives me 2. Okay, Dylan? How many sodiums do I have over here?
2,
How many do I have over here?
1.
So fix it.
Put a 2 coefficient in front of the NaCl.
So now I have 2 AlCl3 plus Na2O yields Al2O3 plus 2 NaCls. I'm not balanced yet. I'm going to go and do my anions now. Rebecca. You there, Rebecca?
Yep.
Okay. How many chlorines do I have?
3.
Ah,
Or 6.
multiply the coefficient times the subscript. I have 6 chlorines. How many do I have over here?
2.
So what do I have to do?
Can you change that 2 into a 6?
Yep, certainly can. Okay, I certainly can, and that is indeed what I did too. Now, Rebecca, I have how many oxygens on the right?
3.
How many on the left?
1.
Okay. What am I going to
2.
do?
Put a coefficient of 3 on the Na2O.
Now I look at it and check it out. I've got 2 times 1 ALs on the left, 1 times 2 ALs on the right, 3 times 2 NAs on the left, 6 times 1 NAs on the right, 2 times 3 CLs on the left, 6 times 1 CLs on the right, and 3 times 1 oxygens on the left, 1 times 3 oxygens on the right. I am balanced, ladies and gentlemen. Questions? Does anybody need me to go through another example? I'll make up one on the fly. Are we good?
I think so.
All right, that's fine. Fine by me, Dana. So we are going to get into something called double replacement reactions. And the first thing I have to do is I have to explain. I have to explain how ionic compounds exist in water. Now, in a regular crystal form, if I have something like sodium and chloride, I have a cation and it is bound to an anion. In the case of sodium chloride, there are 6 chlorines that go around each sodium atom. Now, I also have to understand, remember I told you that there was such an animal as polar covalent bonds?
Yeah.
What a polar covalent bond does is if I have water here, the electrons are spending more time around the oxygen than they are around the hydrogens. This basically means that the oxygen has a negative charge and the hydrogen end has a positive charge. So this negative oxygen is going to go and start working its way in here, and it's going to start to pull this sodium away from the chlorine ions, so that eventually we have sodium that gets surrounded by waters. By the same token, when we have a chlorine ion, that's negative, so the positive end, the hydrogen end, start to go towards the chlorine, and they start to segregate it out. So you get the waters here with the hydrogens facing towards the chlorine, and that gets completely separated out. So that eventually, if the ionic compound completely dissolves, what happens is you get complete dissolution of the sodium chloride into sodium ions and into chloride ions. Now, if I have a reaction and I have one ionic compound and mixed with another ionic compound. I got a beaker of AB and I got a beaker of CD. I mix them together. Amazingly enough, the A sees the D, and that makes a compound that is no longer soluble in water. We have different properties. Both CD and AB were soluble in water. We now have a compound that is insoluble in water. Different chemical properties. We have a chemical reaction. So what is really happening in this is there is a change from one side to the other. I've reacted A plus and D minus to make a compound AD, which does not dissolve in water. Another example, or a more specific example with real chemicals. If I have sodium chloride into a solution, it completely dissolves. So I have a homogeneous solution there. If I have silver nitrate, it completely dissolves into silver ions and nitrate ions. But when I pour it in there, the silver will seek out the chlorine. When they get together, they make a compound that is insoluble in water. We have a chemical reaction taking place. On the other hand, if I mix a compound that is aqueous with another compound that's aqueous, and the compounds that we can possibly form are aqueous and aqueous, nothing has happened. Because if I have my AB, that is broken down into A plus and B minus. My CD is broken down into C plus and D minus. My AD is still at A plus and D minus, and my BC or CB is now at B minus and C plus. The solution doesn't care whether the A plus came from AB or AD, or that the D minus came from CD or AD. There's no change, no reaction.
So would that be a physical change, or is it still a chemical change?
It's not a chemical change, absolutely not a chemical change, because nothing's happening. Okay,
So
that's the first thing.
Dissolving?
Physical change, you're diluting it a little bit. So yeah, I would probably say it's a physical change.
Okay.
Reaction occurs in a double replacement reaction if a solid is formed. The solid is called a precipitate. If a solid forms, these are called precipitate reactions. If you get a change in color, if you mix sodium thiocyanate with iron nitrate, both of them are clear, colorless solutions. But when you mix them together, you form a brilliant blood red color. You had no color before. You have a new chemical property. Therefore, you have a chemical reaction. If you evolve a gas, if you take sodium carbonate and you take sodium carbonate as a solution, and you pour it into hydrochloric acid, you get an evolution. A gas starts to bubble up and foam over. The sodium carbonate didn't have a gas in it. The HCl didn't have a gas in it. As a consequence, the new compound has a new chemical property. Something has changed. Chemical reaction. You can also have an exchange of electrons. That is, we're going to get a little bit into it, but we're not going to get into the real hot and heavy redox reactions. You're going to get those in Chem 2. So how do you know if a solid forms? You know by something called a solubility chart. You have a vertical column in the substance in the graph I'm going to show you in a second. The vertical column lists cations. The horizontal row lists anions. Just basically take your two fingers and make them meet. Now, if I'm looking at magnesium hydroxide, I'm going to take my finger from the magnesium. I'm going to take it over and I'm going to take the hydroxide down. Where the magnesium and the hydroxide mix, I read the symbol. It says S. S is solid. It forms a precipitate. On the other hand, if I have lithium iodide, I take my lithium, take it all the way over to where the iodide is, where they meet. I see that's aqueous. That means it forms ions and dissolves in water. AQ means aqueous. I or S means a solid. D means decomposing. That means something happens that we don't really know what's going on with it. Something funky happens. Remember, we have to balance the individual compounds with subscripts. Once these compounds are balanced, we balance the equation with coefficients. Balance the cations except H, anions except O. Polyatomics go from side to side. If they don't change from side to side, treat them as a unit. Balance the H's, balance the O's, then recheck. All right. How do we recognize something as being a double replacement reaction? Look at this. What type of compounds are these?
Ionic.
They're ionic. If you have two compounds beginning with metals, you've got a double replacement reaction. All right? Now, who's ever watched the Flintstones?
I've
I
seen it
have.
a little bit.
Okay.
Yeah.
Who are the main characters? And do not name Bam, Bam, and Pebbles.
Like
If
Fred
you name
and
Bam, Bam, and Pebbles, you will get me in trouble for something later I'm going to talk about.
Wilma.
Wilma. Who's Wilma hooked up with?
Fred.
Wilma is hooked up with
Fred.
Fred. Okay? Who are the other couple? Ooh.
Barney and
Come on,
Betty.
somebody else. Barney and
Betty.
Betty. All right. I used to watch the Flintstones in the 70s. There was also this wonderful tradition in the 70s called the Key Party. Anybody know what a Key Party is?
Nope.
All right, couples come to one house. And what happens is the husband drops his keys into a big bowl. All the husbands that show up drop their keys into
like
a
a
big
swingers
bowl.
party.
And the wife is blindfolded and she reaches in and grabs a key. Whoever keys she grabs, she goes with that husband. Yes, indeed, it is a swingers party. So we have Fred and Wilma, and we have Barney and Betty. Well, what happens is Betty reaches her hand in there and she grabs Fred's keys. So Betty, being the anion, will hook up with Fred being the cation. The first cation links with the second anion. Similarly, Wilma reaches in and she grabs Barney's keys. So Wilma reaches it in with Barney so that the second cation reacts with the first anion. Please, ladies and gentlemen, cations always get listed first. So if I am looking at that reaction, What I want to do is I want to put the products together. By that, I mean, all I want to do is link the cation with the anion with no subscripts. And I'm going to take the other cation and the other anion, I think it's this one, link those together. That's all I want you to do at this point. Okay? Now, you're going to look at the solubility chart. And you're going to look sodium and nitrate, and you're going to look up lead and chlorine. Okay, sodium down here, and nitrate, aqueous. No reaction so far. We're going to look lead and chlorine. Oh, we have a solid. We have a reaction. Ladies and gentlemen, if you link two things up such that the products that get formed are both aqueous, you have no reaction. All you have to do is put NR. You don't have to do anything more. For example, if I was looking at sodium chloride reacting with potassium bromide, it's right there. Sodium reacts with the bromide to make sodium bromide. That's also aqueous. Potassium reacts with the chloride to make potassium chloride. That's also soluble. So no reaction takes place. So once you get the products put together, then you go to the solubility chart and you figure out whether you have a solid. If you don't have a solid, if both of the new compounds are aqueous, you're done. No reaction has happened. But we got a solid. Now what we have to do is we have to balance the molecules. Anybody know the charge on sodium? Get your periodic charts out, ladies and gentlemen. Charge on sodium.
-2.
What?
That was wrong.
What's your second guess, Joe?
Oh, it's 1 + 1.
+1. Anybody know what the charge on NO3 is?
I think it's
-1.
-1. Is this compound balanced?
Yes.
Okay. Lead is a type 2 compound. We don't know what the charge is, but we can figure it out because conveniently, you all just told me that the NO3 charge was a -1. So if NO3 is a -1, what does the lead have to be?
+1.
How many NO3s do I have?
2.
So what's the total negative charge on the NO3s?
-2.
So what's the charge on the lead?
+2.
Now, these are simple reactions. The oxidation state, the charge, don't forget I said oxidation state, I don't want to confuse you. The charge does not change from left to right. So if lead's a +2 over here, it's going to be a +2 over there. What's the charge on the chlorine?
-1.
So how many chlorines do I need?
1.
Lead's a +2, chlorine is a -1. How many chlorines do I need?
2.
Yeah.
I need 2. Okay. Guys, you have to assume that the reactants are balanced. If you have type 2 cations in there, you have to assume they're balanced because there's no way to do the problem if it's not. Okay? So, balance the cations. Dana, how many sodiums do we have on left and right?
We have 1 on the left and then 1 on the right.
Good enough. They're balanced. How about the leads?
Me?
Yep, might as well.
Okay. 1 on the left, 1 on the right.
We're balanced there too. That was too easy, Dana. You got to do a hard one for me.
Okay.
How about the chlorines?
Chlorines, 2 on the right, 1 on the left.
Okay, so if there are 2 on the right and 1 on the left, what do we have to do to make sure the chlorines are balanced?
Put a big number 2 in front of the NaCl.
Good. All right. Now let's look at the nitrates. Nitrate change from left to right?
Yeah, there's 2 on the left, 1 on the right.
No, but does it change? Is it still NO3 left and right?
Yeah,
So if it's NO3, we can treat it as a unit. Now, how many NO3s do I have on the left?
2,
How many do I have on the right?
1.
So what I'm going to do is I am going to put a
2 on the right.
yes, absolutely.
Why don't we just get that from balancing equation, I guess?
I'm sorry, Joseph?
If you go back, so NO3, you know, Na has like a positive 1 charge, and NO3, oh wait, not mine. Looking at the wrong thing.
Okay.
Oh, good.
I don't like myself being confused, so. All right. Joe, predict the products. All right, no, first, let's do it this way. Do I have 2 ionic compounds?
Yes.
If I have 2 ionic compounds, I have a double replacement reaction. Put the products together, do not add subscripts.
Whatever BA is, BaCl2.
No, I want you to predict the products.
Yeah, I messed up. BaSO4
BaSO4 and
plus K2Cl2.
no, you don't carry over the subscripts. Just put the things together.
KCl.
KCl. All right. So we have barium sulfate and KCl. Now we got to see if these are balanced. Blake, do you know what the charge on barium is, Blake?
Let's see. It's going to be a -2 or +2.
+2. Do you happen to know what SO4 is?
I'm going to go on a limb and say -2.
If you go absolutely crazy and your head goes like that, you can figure it out because look what I gave you. I gave you a balanced chemical over there, right?
So it's not normally in a K2 state?
I'm sorry?
Or no, I'm sorry. Go ahead. Go ahead.
So if you don't know what the charge is, sometime in the future, if you get a teacher that doesn't allow you to know, that makes you memorize the charges, and you forget what SO4 is, use what the test, this is honest cheating, guys. Because look at this, you know K has to be a +1. There are 2 of them and only 1 SO4. So you can use this to deduce that SO4 has to be a -2. Thought I'd give you that little bit of information. Use the test, guys, because the test provides you with information you're not even knowing it that is there. So barium sulfate, +2, -2, balanced. What about KCl?
KCl is in like the charge for it, or what it balance as?
What's the charge on K?
Charge on K. Let's see.
+1.
+1. And
Yep.
Cl?
-1.
So do you see, who was it, Blake? Were you
I was
trying to
just-
do K2Cl2? Who was trying to do K2Cl2?
That was me, I think. Yeah, Blake.
Okay.
Confused.
Do you see now why you don't carry over the subscripts?
Oh wait, no, that wasn't me.
Yeah, that was me. But
I don't care. I don't care. I'm not taking notes on this. So, I literally speaking, are you all aware of why you don't carry subscripts over from
but
the?
if
Yes.
it's been like +2, -2, then
If it's a +2, -2, it'd be like barium sulfate. As long as the charges are the same between the cation and the anion, the subscripts are always going to be 1 and 1.
I mean, if I brought over the Cl2 and then K2, wouldn't it still be the same thing? Just
No, different molecule. The molecule you're suggesting has 2 potassiums and 2 chlorines in it. When in actuality, what the molecule is 1 K and 1 Cl. Does that make sense to you, Joseph?
Yeah, I get it.
Okay,
Blake here. I've got a question though.
sure.
SO4, we're just supposed to know that that charge is -2.
Yes, literally speaking.
So that's one of the polyatomic charges that you need to memorize. Gotcha. Okay,
Yeah.
so
Should
that's
be
what
there,
I'm
yeah.
lacking.
Remember,
Gotcha.
I'm not making you memorize it. You can put it on a piece of paper somewhere. Okay? But
Copy that.
again, even if you didn't know it, you know this compound is balanced. You can deduce the charge on the SO4 because you can look on the periodic table and see what K2 is. Does that make sense to you?
Absolutely. Yep.
Okay. Now, the other thing I have to do, I have to look at these 2 compounds and I have to figure out whether a reaction occurs. Okay. Potassium chloride. What is it, guys?
Aqueous.
All right. So we got to look at the other one. Barium sulfate. Do we have a reaction?
Yes.
Yeah.
All right. So we have, I'm sorry, I'm predicting your products. Had to find out where I was. All right. Let me see who I haven't picked on yet. There's somebody at the very bottom. David. You there,
What's that?
David?
Yeah, I'm here.
Okay, we're going to balance this equation. BAs, left and right. How many BAs on the left? How many on the right?
There's 1 on each.
How about the Ks?
There is 2 on the left and 1 on the right.
Fix it.
Put 2 in front of the K.
Which K?
This is the one on the right.
Guys, when you're answering that question, say KCl, all right?
Okay. So 2 in front of the KCl.
Thank you so much. So I put 2 in front of the KCl. All right. Now, I'm sorry, that was
David.
David. Thank you. I'm sorry. Lost my presence of mind there for a second. So now we have done the cations. We got to go back and look at the anions. How many Cl's on the left, David?
2.
On the right?
2.
We're good. How many SO4s?
1 on each side. There's 1 on each side.
Are we balanced?
Yes.
That's a crappy one. I don't like that one. All right, predict the products.
Silver chloride.
And
Sodium nitrate.
is one of those a solid? Silver chloride and sodium nitrate.
Silver chloride is.
Silver chloride. So do we have a reaction?
Yes.
Yeah, this is boring. It's boring because what you get is AgCl and NaNO3, and it's already balanced.
Mm.
Predict the products. Dylan.
AlNO3,
And
ClPb.
PB goes first. The cation goes first. So I have my two things together. Now I'm going to go back. Okay, Dylan, we had PbCl and we had something else. Aluminum nitrate, right?
Yeah, right.
We have aluminum nitrate and PbCl. So we're going to go to the solubility chart. Aluminum nitrate and PbCl. Is one of those a solid?
PbCl will be.
Do we have a reaction then?
Yes.
Yes.
Okay, so sorry, I got too far. All right, now we got to look and we got to balance the chemicals. What's the charge on Al each and every time?
+3.
NO3?
-1.
So how do I balance AlNO3?
You need to put a 3 after NO3.
Parentheses, then the 3. Okay? What's the charge on the PB here? If you said NO3 was a -1, what does the charge on the PB have to be?
+4.
So if PB is a +4, chlorine was a -1, how do you balance that?
Put a
CL4.
Cl4.
Oh.
So now it's the chemicals are balanced. Now we got to figure out the anions and cations. Looking at it, are the cations balanced? Men,
Yeah.
are
Yeah,
the cations, are the ALs balanced, men?
Put
Yes.
3 in PB
Okay.
and
I'm sorry, somebody ask a question?
Thinking
Okay.
with it.
I'm sorry, Joe, I didn't hear you.
No, nobody asked a question.
All right, men, back men. Are the
Yeah,
PBs
yeah.
balanced?
Yes.
Okay. How about the chlorines?
No.
3 and 4.
Okay, what do I have to do? What do I have to put in front of the AlCl3?
A 4 in front of.
4.
Let men answer, please. Men,
Yeah, put 4 before AlCl3.
and what are you going to put here?
3.
3? Okay, men,
Mm-hmm.
I have 4 NO3s and 3 NO3s. What goes in front of this one?
A 3.
3
And this one, men, let men answer.
4 Al.
4. So I end up doing that. I've got 4 AlCl3s, 3 PbNO3s, 4 AlNO3s, and 3 PbCl4s. Are we pretty good with this, ladies and gentlemen?
Yes.
This should be pretty much a review from intro or from your academic high school course. Should be pretty much a review. Okay? And I'm going to go through and review it again. You recognize a double replacement reaction because on the reactant side, you have 2 ionic compounds. What happens in a double replacement reaction? The first cation reacts with the second anion. The second cation reacts with the first. Just put them together. Put the 2 things together at first. Then what you do is you go to a solubility chart. In this case, I looked up PbCl4, and I know that that is a solid. So I know a reaction happened. The next thing I do from there is I look at each individual compound and I balance them. Balance the chemicals themselves. Remember, do not carry over subscripts. Once the chemicals are balanced, I balance the cations first, anions, hydrogens, then oxygens, then check it. Okay, another thing that happens, I have to record the states of the reaction chemicals. If I don't record the states, I can't say if a reaction has happened or not. If I don't say in those double replacement reactions that a solid was formed, I don't know that it was a reaction. So you have to include the states of the reaction chemicals. All right, Rebecca.
Yes.
Predict the products. First one.
BaCO3
And?
NaCl.
Good. We're going to go with who's next? I need more of you people in here so I don't pick on people all the time. Ben. Ben. You there, Ben?
Yes.
Okay. Second compound. What are the products?
AgCl3.
No.
Okay.
Remember, Ben, you don't carry over the subscripts.
Oh. Would be 3 AgCl3.
AgCl.
AgCl,
You're
okay.
not balancing it yet, Ben. You're just predicting the products.
Okay.
So you have AgCl. What else do you have in there?
NO3Fe.
All right. Again.
Oh, NOFe.
Fe goes first because that's the cation. Okay? You
Okay.
always put the cation first. Okay? That makes sense, Ben?
Yes.
All right. Now, if I was looking at this, I have Ag. Do you know what the charge on Ag is, Ben?
No.
It's one of the ones that you have to know. Somebody help her.
+1.
Ag is a +1. Ben, do you know what the charge on Cl is?
1 negative.
So if you have Ag as a +1 and Cl as a -1,
It's balanced. Oh,
it's
wait, no,
balanced. So, and remember, Ben, you wanted to put the 3 from the Cl over there.
yeah.
We are going to fix that later on with coefficients. Okay? But
Okay.
for now, the Ag and the Cl just exists as AgCl. Okay. You just told me, Ben, that the Cl was a -1. If Cl is a -1, what is the charge on the Fe?
+3.
Okay, so if Fe is a +3 and NO3 is a -1, how many NO3s do I need?
3.
Okay, so now we have this reaction going to AgCl plus FeNO3 taken 3 times. All right, my Ags are balanced, my Fes are balanced. But I have 3 Cl's on the left. I only have 1 on the right. So what number goes in front of the AgCl?
3.
3. So I now have 3 chlorines on the left, 3 on the right. Okay. Now the other compound is FeNO3 taken 3 times. How many NO3s do I have on the left, Ben?
1.
How many do I have on the right?
3.
What number has to go in front of this?
3.
So I have 3 AgNO3s plus 1 FeCl3, yielding 3 AgCls plus 1 FeNO3 taken 3 times.
Yes.
Guys, do I need to go through any more examples?
Not here.
I don't think so. I don't.
If you need it, let me know. I'd be happy to do it. Okay, having heard that, we're going to go into ionic and net ionic equations. Ladies and gentlemen, have any of you driven over that horrific bridge called the Howard Franklin Bridge?
Yes.
Okay, have any of you been stopped before the hump on the Howard Franklin Bridge and are just inching along?
Yep.
Yep.
The more I inch along, the bigger my ire gets. And I need a reward because I am getting frustrated. I need a big reward. So as I'm driving over the hump and inching along, I better damn well see some blood. I want to see a bloody accident, ladies and gentlemen. I want some entertainment for my frustration. Now, as I am driving along, and I'm looking over there and I'm finally seeing my bloody accident. Did I cause that accident?
Yes.
That's a Schrodinger's cat question.
I didn't, wait. I didn't cause that accident. I may cause another one, but I didn't cause that one. Right?
We can say that.
So if I didn't cause that, all I'm doing is what with that reaction, with that accident? All I'm doing is what?
Looking at it.
Looking at it. I'm spectating.
Reacting.
I have nothing to do with that accident. Another example. Ladies and gentlemen, you are up on the 60th row in the high part of Raymond James Stadium last year. You are there just as you witness Mr. Winston throwing a pass right in the belly of a linebacker, who then proceeds to take it all the way back the other way for a touchdown. Now, did you have anything to do with throwing the pass or catching it? What is your role in that stadium?
As a spectator.
Spectating. You have nothing to do with what went on. Chemicals are no different. Chemicals are no different. Okay? But in order to do that, we have to get down real dirty and figure out what's happening. What we do is we have to take out, we have to see what these things are. If it says aqueous, what that means is this compound doesn't exist as AlCl3. It exists as an Al and 3 Cls. An Al plus 3 and 3 Cl minuses. But even in fact, that's not even true, because this coefficient in front tells me I have to multiply 4 times the subscript. I've got 4 aluminums. The charge on that aluminum is a 3+, and it is in the aqueous state. I need to identify each ion by 4 things. The number of them. I get the number by multiplying the coefficient by the subscript. I have to put the chemical symbol of that ion. I need to put the charge, and I need to put that it is aqueous. Don't get intimidated by this, ladies and gentlemen. It's not that hard, because if you look at the compound, the first element, if it's a metal, is the cation. Everything else is going to be the anion. So if I take this compound, this 4Al3 reaction, I can break the AlCl3 down to 4 times 1, 4 Al, 3 pluses, aqueous, plus, now I go 4 times 3, 12 Cl minuses that are aqueous. Again, remember, number, symbol, charge, state. This one, the lead nitrate. I'm taking the 3, multiplying it by the 1. I'm getting 3 leads. I'm looking at the charge. The charge on this is a 4 plus. It's aqueous. Again, I look to 3 times the subscript 4. I have 12 NO3s, 1 minus, aqueous. That's yielding. I look at this compound. I have 4 Al, 3 pluses, aqueous. 4 times 3, 12 NO3 minuses, aqueous. Now I come to the solid. All these other things are aqueous. They split into their ions. This one specifically is a solid. It stays together so that I have 3 PbCl4s as a solid. Are we understanding what is going on with this?
Yes.
Does this make sense, everybody?
Yes.
Roger Dodger.
Now, I got to look at this reaction. If I look in a reaction and something is the same on the left and the right side of it, I can cancel it out. What is the same on the left and right side of this equation?
Aluminum, aluminum and
fours?
yeah, and the nitrate.
And the nitrates. So I go and do that. I go and do that. I eliminate the aluminum. I eliminate the nitrates. What's left? 12 Cl minuses aqueous plus 3 Pb4 plus aqueous, yielding 3 PbCl4s. That is what is really happening. The only reason the Al exists is to deliver the Cl minus. The only reason the NO3 exists is to deliver the lead. Other than that, there's nothing happening with them. We can eliminate them. And once we eliminate them, we have the net ionic equation.
I have a question.
Yep, I'm here.
Are we allowed to simplify that?
This one?
Yeah. Are we allowed to like take 3 out of everything or no?
No, you can't.
No?
You can't do that. Because of the fact that you can't. Good question, Joseph. That is a good question. For now, just assume that you don't change it, okay?
All right.
Do I need to go through another example of this? Or, nah, we're going to do that, yeah. All right, let's go through. Rebecca, NiBr2. What does that break up into? How many NIs do I have?
1,
What's the charge?
2 plus,
And what state is it in?
aqueous.
How about the BRs?
2 minus, aqueous.
How many of them?
2.
Okay. Dana,
Yes.
sodium carbonate. What does the sodium carbonate break into?
2 Na plus aqueous and carbonate 3, or just carbonate minus 2 aqueous.
Okay. Joseph,
Yellow.
what does the NABR break up into? It's aqueous. I didn't mark it on there. It's aqueous. And the NiCO3 is solid.
2 Na and BR.
How many BRs?
1.
Joseph, we multiply the coefficient times the subscript.
Oh, yeah, 2. Yeah.
2. And Joseph, don't get lazy on me. You have to say specifically 2 Na 1 plus aqueous plus 2 Br minus aqueous. All right?
Right.
Dylan, do we break up the NiCO3?
No,
Why?
because it forms a solid.
It formed a solid. Okay. I didn't want to do that. So I got to figure out who else is in here. We'll go with Min. Min, you there? I still see 9 people, man. Okay, Blake. Blake,
Yeah. What's up?
is there anything that's the same left and right on this equation?
Yeah, the 2 Br minus and the 2 Na plus.
So I can
Cancel those.
cancel them. And I am left with Na, 1 Ni plus 2 plus 1 CO3, 2 minus, yielding 1 NiCO3. Ladies and gentlemen, are we good with this?
Yep.
Okay, we're going to get through single replacements. All right, single replacement is, you recognize them by having one ionic compound, and to that ionic compound, you're adding a neutral, either a neutral diatomic molecule or a neutral metal. Okay, the neutral diatomic is going to be a halogen. And they exist as diatomics, as I2, Cl2, F2. So what happens when I have a halogen? A halogen can't possibly make a cation. A halogen can make an anion. So I have to look, and I have to compare the anion that is already in the ionic compound to the halogen that is there. If the halogen is more active, it will become negative and it will replace the original anion. So if I have AB plus C2, what it ends up happening is the C replaces the B. I have AC plus the B now becomes neutral. If it's a halogen, it's going to be B subscript 2. On the other hand, if I have a metal, metals can't be anions. Metals can become cations. I look at D and A. I decide if D is more active than A, D will replace A. I get a compound DB. D now has lost its electrons and given them to A. I make a compound DB. The electrons that D has given to A have made A neutral. Remember, the more active species will always end up being ionic. By that, I mean it will end up having a charge. You don't have to copy it down. If you just remember that this is in the reactions PowerPoint and it's in the single replacement, just note that this is there, or you can find it from another source. Anions. Fluorine is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine. So fluorine's going to want to be negative the most amongst those 4 things. That's an easy way to remember that. Again, The more active element will always end up in the ionic form. That's rule number 1. Rule number 2, if the reaction occurs, then the reverse reaction will not. By that I mean, if I react sodium iodide with F2 and I get a reaction of NaF plus I2, what this first statement means, I can't add NaF and I2 and get a reaction to go. On the other hand, if a reaction does not occur, then the reverse reaction will. By that I mean, if I mix sodium chloride and silver, I do not get a reaction. But if it would have gone, I would have had silver chloride and sodium. The sodium will react with silver chloride to replace the silver and make sodium chloride and silver. So what's happening in this? Again, Fred and Wilma. Fred and Wilma are together. Wilma looks over, sees Barney. She says, I like the looks of a short, dumpy blonde guy. This fat old brunette that's over here, I'm dumping him. And I'm going to go with the short, dumpy blonde guy. And so I'm going to react and I'm going to make a DB. Poor Fred, sitting off by himself. If I want to look at the ionic equation, I break up the ionic compound to A plus and B minus. D stays because it's a neutral compound. Now, what happens? Remember, D gave up its electrons. It gave up its electrons to A. So D is now charged. It reacts and it's made D plus and B minus. A, because it's gained the electrons from D, is now neutral. If we look at the net ionic equation, B minus cancels with B minus. And overall, what really is happening is I'm getting electrons moved. I'm getting electrons moved from the D atom to the A atom. D is now becoming positive. A is now becoming neutral. That is all that's happening in a single replacement reaction. Okay, Dylan. You're adding Na to CuCl2. You know this is a single replacement reaction because you have an ionic compound to CuCl2 and a neutral metal. You know that the sodium is more active than the Cu. And you also know if a compound is more active, it makes that compound, if an atom is more active, it makes that atom ionic. So Dylan, does a reaction go?
Yes.
Reaction goes. So I have my CuCl2 plus Na. Na displaces the Cu. I now get NaCl plus neutral copper. Because there are two Cl's in the CuCl2, I have to put a 2 in front of the NaCl, and that balances with the 2 in front of the Na. Ionic equation, I split this up to Cu2 plus 2 Cl minuses. Yeah, I got lazy. I didn't put the states in there. Plus 2 Nas. What this does is it makes 2 Na pluses plus 2 Cl minuses plus a Cu. Blake, is there anything that's the same on the left and the right?
Yeah, the 2Cl negative.
Is that the only thing that's the same?
Yes.
So my net ionic equation is Cu2 plus 2 NAs yielding 2 Na pluses plus Cu. But the reverse, if I mix 2 NaCl's plus Cu, that reaction does not go because Na is more active than Cu. Na is already ionic, so it's not going to do anything. Predict the products. Min, you're back. Min? Okay, let's go. Somebody else, somewhere else. Ben. Ben.
Yes.
Okay, you have copper or calcium with aluminum sulfate. Calcium is more active than aluminum is. What are the products?
CaSO4. Three.
What else?
And Al.
And Al. Okay. Now I got to look at my ionic compound, CaSO4. Is this balanced?
No.
What's the charge on Ca, Ben?
2.
And the SO4?
-1.
Nope.
No.
Nope. It's a -2.
Oh, -2.
So is it balanced?
Yes.
And the Al?
Al.
Al's neutral. Okay. If you just have a neutral metal, you just list it down there.
Okay.
Okay. Now, Joseph, these are my
Yes.
reactants. These are my reactants. These are my products. My products are now balanced. Are my CAs the same?
Yes, they are.
My ALs?
No, they are not.
What do I have to do?
The 2 by the Al.
Okay. I have to put a 2 by the AL. All right. Are my sulfates balanced?
No, they are not.
What do you have to do?
Put a 3 by CaSO4. The right side.
Now, have I futzed up with something?
Yes.
What's
You
the last thing I
3
have to do?
Ca, so put a 3 by the Ca. Left side.
Are we good, guys?
Yep.
We're at the end of our time here, guys. What I'm going to do is I'm going to begin the next lesson. This is where I got to in the morning class. So I'll begin the next lesson with this slide. Fair enough?
Word.
I'm sorry?
Sounds cool.
Okay. Ladies and gentlemen, I will see you next Tuesday.
Perfect.
Hello. See ya.
Did that work? Did you understand a little more? Did that work, guys? Or am I going too
It's
slow?
perfect.
Yep, that worked.
No, it's perfect. It's fine.
Okay. Good enough, guys. Please give me criticism, critique me. Make me go slower, ask questions. I got further than I thought I would. I didn't think I'd get through single replacement reactions. So I got further than I thought I would. David?
I was just going to say this is all semi-review. And I don't know about everybody else, but I just took my intro to chem class, so.
Okay. And great. Absolutely great. All right, ladies and gentlemen, that's all I got. So, and show, I will see you on Tuesday, guys.
Perfect. Have a good weekend.
Anybody
right.
have anything they want to discuss?
I don't.
Okay, Dana, what's going on?
I said I don't.
Oh, okay. If literally speaking, if you don't have anything else, I like to ask this question because some people want to talk privately, and so they wait till everybody goes off and then speak up. Bye.